summary in English. Please.
Thank you. What you see here in these flasks, ladies and gentlemen, are quantum dots in a liquid solution. Well, you don't actually see them because they are truly tiny. They are what we call nanoparticles, only a few millionths of a millimeter in size. Each particle is a small crystal containing just a couple of thousand atoms. When things become this small, quantum mechanics starts to play all kinds of tricks. The nanoparticles in each flask are made of exactly the same simple substance. So how can they differ in color? Well, that, ladies and gentlemen, is a quantum effect. The particles are so small that their electrons start to get crowded. The smallest quantum dots shine in blue, while the bigger ones shine in yellow and red. They only differ in size, nothing else. And the size changes a lot of their properties: thermal, electric, magnetic, etc. The first observations of this effect were made by two of this year's laureates. Alexei Yekimov saw it for copper chloride nanoparticles immersed in a glass. And Louis Bruce observed it for nanoparticles floating freely in a liquid solution. For a long time, nobody thought you could ever actually make such small particles, but this year's laureates succeeded. However, for quantum dots to become really useful, you needed to be able to make them in solution with exquisite control of their size and surface. Munji Bawendi invented an ingenious chemical method for doing just this. He could now make perfect nanoparticles of very specific size and very high quality. These achievements represent an important milestone in nanotechnology, and today there are numerous applications of quantum dots, ranging from QLED screens to imaging in biochemistry and medicine and much more.
Thank you, Professor Åqvist. And now, Professor Heine Linke will give us a more detailed presentation. Please.
So let me first check the sound works, yes. So the discovery we just saw, and what you also have on the screen, that in the same material, a larger particle can have a red color, a smaller particle can have a blue color, is at its core a quantum mechanical effect. Quantum mechanics predicts that if you take an electron and put it into a small space, the electron's wave function gets compressed. And the smaller you make the space, in this case the particle, the larger the energy of the electron. If you can store more energy in an electron, it can also give more energy to a photon. So the light emitted from a small space, electron in a small space, will be more blue, and that from a larger space will be more red. And this is what you can also see in this animation. So again, if we confine an electron, that's the wave, in a larger particle, it can be more red. But as you compress, imagine making smaller and smaller particles, compressing the wave function more and more, you give the electrons more energy and they send out more blue light. In this sense, quantum dots are a new class of materials. They are different from molecules. If you imagine if you wanted to make different colors with molecules, you would, for each color or for each other property, you would choose a new molecule, a new set of atoms in a new constellation. Quantum dots, however, have all the same structure. They have, in fact, the same structure as a bulk material would have. It's the same atoms in the same constellation, just that a small dot has fewer atoms and a bigger dot has larger atoms. The fact that they then change properties is not only their color, it's essentially every property, every material property you can think of, including electric, optical, magnetic, even catalytic effects, how they influence chemical reaction, even the melting point changes. So in this class of material, you have found a way of changing material properties not by changing the material, but just by the size. And this is a foundational discovery in nanotechnology, the ability to do this in a controlled manner using quantum mechanical effects. The prediction that this would be possible, the prediction that such an effect could occur in theory was made as early as the 1930s. But for the next 5 decades, it seemed near impossible to make such materials because not only do you need perfectly crystalline structures, and you need to control the size exactly, basically atom layer by atom layer, you also need a perfect surface property so that you can get these phenomena and these clear colors. This was not actually expected to be possible. The discovery that this is indeed possible was first made by Alexei Yekimov, who studied colored glasses. And by adding copper and chlorine to a glass, he was able to show first that the copper chloride formed as nanocrystals, so crystals with crystalline properties. He used deep insight into the physical chemistry to control the size exactly, was then able to show that the color of the glass correlated with the size of the particle, and not just in any way this straight line there means, because the straight line is a smoking gun, that this is a quantum effect. So all of this was done in one sweep of results. The discovery was made a second time in a different context by Louis Bruce in the United States, this time for particles in solution, freely in solution, available for further processing. This was done in the context of studying semiconducting particles for their catalytic properties. The vision was, and still is, in fact, to use light, such as solar light, to drive chemical reactions. So it's a form of solar energy conversion. He looked at relatively small particles and again noticed that the optical properties changed with size. This triggered a lot of interest. Just imagine the ability to suddenly be able to tune material properties not only by making new materials but by their size using quantum phenomena is of course very inspiring and triggered a lot of interest to see what could this be used for. But for the next 10 years, this was difficult because the size was not quite well controllable enough. The quality was not quite good enough for real applications. Munji Bawendi discovered or invented a method for making these particles in a much more controlled manner. The trick being to precisely control the moment in time when nucleation, the beginning of the particle growth, first changes. So he used a hot solvent, well-chosen solvent, and at one instant suddenly injected the reagents, which led to an instantaneous formation of small embryo crystals, a nucleation event. But then the growth stopped because the solution was diluted and the temperature dropped. By reheating and carefully controlling the temperature, again with deep insight in the growth processes, it's possible to control not only the size, but also keep the size in a very narrow window so that only one size gets produced. And the solvent was chosen such that the surface of the particle was protected and gave a very high quality. This opened then for the possibility of applications. And today we see commercial applications, for example, in TV screens, where quantum dots are used to produce the RGB colors that make up every pixel. We see them in illumination sources where the LED light, the blue LED light, gets converted into a light that is perceived as pleasant by humans. It's also used widely in biomedical imaging, in this particular example, to visualize the vascular system of a tumor. But this is not where it ends. Research is still very intense, and there is applications expected or being heavily researched in producing photons for quantum communication, for flexible electronics, for sensors, for improving solar cells, making them better or cheaper. And not the least, the same that also Bruce had been working on, namely catalysis for solar fuels, among many other things. So for these reasons, the Nobel Prize in Chemistry for 2023 will be awarded to Alexei Yekimov and Lou Bruce for the discovery that it is possible to make such quantum dots, and to Munji Bawendi for a synthesis method that made quantum dots widely useful.
Thank you, Professor Linke. We shall see now